Hello friends, welcome back to the supplementary video lecture series. In this, our today's topic is analysis of continuous beam using moment distribution method. In the earlier video, we have discussed about the one of the practice example of the moment distribution method. Today we have to see another practice example, but in this, we are going to consider the secondary effect. That is a rotation of the support or settlement of the support. How it is going to consider in a moment distribution method. So let me see the practice example of it using the moment distribution method. So here data is analyze the beam shown in figure. If support B is rotated by 0.005 radian in counterclockwise direction, take EI equal to 18,000 kilonewton meter square. So this is a continuous beam. Three span continuous beam is given over here. Span AB and BC is subjected to the 20 kilonewton per meter UDL over the entire span, while 12 kilonewton 2-point load at a 1 meter distance is given in the span CD. So how to consider the effect of this support rotation? That is the important thing only. Otherwise, the method is the same as we have considered in the previous example of the moment distribution method. So let me start with the first step, that is a fix and moment. So in the fix and moment, we are representing over here in a different way. Either we can show it in the form of the equations or we can show it in the form of the figures. So here we are separating the different span and different loading. For the span AB, the 20 kilonewton meter per meter load is acting over the 4 meter span. So what is the equation? You know, there is a WL squared by 12. So left hand side is a minus or anti-clockwise, right side plus or clockwise. So it is a 26.67. Similarly, span BC, if we see, so it is the same load is applied, so the same equation will be applied, only the length is different. So on the left hand side, minus 41.67, right hand side, plus 41.67. In the CD span, there are 2-point loads, so we are separating this 2-point load. Only if we are considering the 1-point load over here, which is acting at the 1 meter from the left. So what is the WAB square by L square, right side W S square by L square. And similarly, on the second point load, the distance will be interchange. So the moment will be like interchange over here. So this is a fix and moment due to the loading. Now, second thing, we have to consider the effect of the support rotation. So how to consider it? So here, as we have discussed, whenever if it is a one span or two span, right, here it's a support B is a rotating, so it is effect of the support rotation will be in the both the span BA and BC. So if the support is a rotate in the anti-clockwise direction, all the moment will be anti-clockwise in the AB and BC span. So all four moments are anti-clockwise. And what is the moment? In the near end, that is a 4EI theta by L, and on the far end, it is a 2EI theta by L. So if we apply the EI, theta, and L value in the individual span, so what we are going to consider that moment at AB, that is a 45, 90. Similarly, at the BC, there is a 72, and half will be 36 on the far end. So here we have all the moment. Either you can write in the form of the equation or you can represent like this in the form of the figure. We have to do the addition of this moment according to the sign. So first, if we can consider the moment at AB, so it is a 26.67 plus 45, both are anti-clockwise. So it is a minus 71.67. While moment at BA, so it is a 90 is anti-clockwise, while 26.67 is a clockwise. So net moment is a minus 63.33 anti-clockwise. MFBC, both are anti-clockwise, 41.67 and 72. We have to just do the addition of it. So it is 113.67 minus, that is anti-clockwise. Fourth one, MFCB, there is a 41.67, there is a clockwise, and 36 is anti-clockwise. So net moment will be 5.67 in the clockwise direction. Moment at CD, there is no effect of the support rotation in the CD span. So only we have to consider the effect of the loading. We have to do the addition of this. So 5.33 plus 2.67, both are anti-clockwise. There is a minus 8 and last is a 8. So this is the final fix and moment. So what you can see the difference over here, that in the case of the slope deflection method, in another video you have seen that whenever we have to consider the support settlement or rotation effect, so that we have to consider in the slope deflection equation. While in the case of the moment distribution method, we don't have an equation, but we have to consider that effect in the fix and moment itself. So that is one of the difference in the both the method. Next, as we have seen the effect of the distribution factor, so let me discuss about the distribution factor for this one. At support A, as it is a fixed end, so it is a distribution factor is a 0, while support D is a and support is a hinge, a simple support, so it is a distribution factor is a 1. Now if we talk about the B, so member is a connecting BA and BC. BA far end is a fixed, so what is the stiffness? 4EI by 4. And BC far end is an intermediate support, so it is a considered as a fix only, so it is a 4EI by 5. So total summation is a 1.8 EI, and if we do the ratio of the individual one, we'll get the 0.56 and 0.44. Make sure that always the summation of the distribution factor at the any joint, intermediate joint, should be 1 only. CB, if we talk, so far end is a B, which is an intermediate support. So here again, it's a 4EI by 5, and CD end support is a simple support. So what is the stiffness? 3EI by L. So 3EI by 3, that is a 1. So again, summation is a 1.8, and individual stiffness ratio will be nothing but 0.44 and 0.56. We have to apply this distribution factor in the form of the table. So first line members, then second there is a distribution factor at A, it's a 0, DC there is a 1. Now we have to mention the friction moment, which we have find out considering the effect of the support, rotation as well as the loading. So there is a this friction moment equation values we have taken from the step number 1. Now whenever we have a end support is a hinge, simply support, or if it is a overhang, so first we have to balance or that particular end support. If it is a both side is fixed end supports, so we can start from the middle any of the joint. But as you know here, the support D is a and support is a simple support, so we have to balance that joint, and that balancing is also considered as a end correction. So what is the meaning of the end correction? That here if you take a first balancing of the joint D, here 8 we are having the moment, 8 multiplied by 1, so it is a 8, and here we have to write the minus sign as it is the opposite sign, so it is a minus 8, and half moment will be going to carry over on the far end, that is a minus 4, which is called as a end correction or balancing of the end support. So we have to do the summation of these moments, which is a considered as an initial moment. So AB, BA, BC and CD, whatever moments are there, that is remain as it is in the CD, that is the summation of the moment, minus 8 minus 4, that is become minus 12, and DC, that is a 8 minus 8, it's a become 0. So that's the initial moment which we have to consider at the end for the summation. Now end correction is done. Now we have to start with the calculation of the support B and C balancing. So first, if we are going to calculate the BA and BC, so what is the summation of the BA? Minus 63.33 minus 113.67. So total will be minus 177. As it is a minus, we have to write the balancing moment as a plus. So 177 multiplied by 0.56. So we are getting the 99.12. Similarly, 177 multiplied by 0.44. So in the column of the BC, we have to write 77.88. Same manner, if we are considering the balancing of the joint C, so it is a 5.67 minus 12. So we get minus 6.33. That minus 6.33, as we are getting the minus, we have to write the both the balancing moment is a plus. So if you do the 6.33 multiplied by 0.44, so it is a 2.785. While 6.33, if you are multiplied with the 0.56, it will be 3.55. Same way, like in the previous example, here we have to do the distribution or carryover moment. So carryover moment will be on the all the far end. BA will be carry over on the AB 99.12, half will be 49.16. BC and CB will be carry over to each other, so that half of moment we have to carry over, and CD will be not going to carry over because the end correction is already done and far end is a hinge, so there is no carryover moment on the far end. So that is a summation, that's a carryover moment. Now as you can see here, there is no carryover moment due to the distribution factor is a 0. So at the BA it is considered as a 0, and at the BC it's a 1.392. So if we do the cycle, next cycle of the iteration, that's a 0 plus 1.392, so it's a 1.392. So we have to write the minus over here, 1.392 into 0.56, so it will be minus 0.78. And same way, if you are doing the multiplication with the 0.44, so it is a minus 0.78. 612. Same way, we have to do the balancing of the joint C by considering the 38.94 plus 0. So it is a this two value. So we have to do this kind of the balancing and carryover cycle repetitively. So again, we have to do the carryover on the like we have done in the first cycle. Again, we have to do the balancing of the joint B and C, carryover, balancing, carryover, balancing, and we have to do up to the whenever the balance moment is a nearby zero or it is almost zero. So as you can see here that here we are reaching the 0.01, so we have to thus just do the carryover in the final time, and now we have to do the we reach up to the zero at this location, so we have to stop the iteration cycle. Now we have to do the summation of the all the columns, individual columns. So what is the moment, total summation of the moment over here? Let's calculate. So first there is a minus 20, second 40, third minus 40, fourth 31.14, CD that is a minus 31.14, and DC will be remain 0 as it is. So this is our final moment. If we show it in the form of the diagram, so first it is a anti-clockwise, second clockwise, third anti-clockwise, fourth clockwise, fifth anti-clockwise, and last is a 0. So all the moment having the hogging nature, all the minus moment at the support. So we have to connect the minus 20, 40, 31.14 and 0 in the straight lines. Over there we have to show the simple moment of the span moment. So it is a UDL of the WL square by 8 in the both the spine, while 12 kilonewton point load is acting on the last. So it is a symmetric load. So here it is a kind of the trapezoid having the maximum moment as a 12 kilonewton meter. So this is about this practice example, and the main purpose of this example is that how to consider the effect of the support settlement or rotation in the case of the moment distribution method. So same thing will be happen with the support settlement. You have to apply the equation of the support settlement at the particular locations in the fixed moment itself. Now we are going to end this with this one review question, that if you consider the four span continuous beam having the equal span, equal supports up to the end, and equal uniform loading, so the how to solve it using the moment distribution method, because it will be look like a four span but it will be become very much easier. So you should try it with a considering any of the load or any of the span, and you will get the bending moment diagram and shear force diagram, something like this. So the question is that what observation is there from this diagram? What is your observation from this diagram? You can mention in the comment section. So with this, we are going to end this. If you have any doubt, any specifically doubt or suggestions or feedback, you may most welcome for the sharing with us in the comment section. So with this, goodbye. Stay healthy, stay safe, take care. Thank you so much.